All right, so in order to make a lot more progress in the study of Lie group theory, it's become evident to me that we really kind of need to back out into representation theory. And to get into representation theory, it makes perfect sense to spend some time going all the way back to group theory. The problem is people learn group theory in small chunks. You learn about the definition of the group, right? You learn about subgroups, right? You should learn about quotient groups, right? G by some normal subgroup H. You know, you learn various rules, and there is a core foundation of these things, a core foundation of information that everybody probably is exposed to at some point. The question is, the issue is that you forget a lot of it, right? Like, for example, there's a ton of different subgroups that are really important. There's normal subgroups, that's really critical. There's normalizers, right? There's normalizers. Here's just a bunch, right? Normalizers, central subgroups, centralizers, characteristic subgroups. There's others too. Silo subgroups. We'll talk a lot about silo subgroups here. So we easily and quickly forget what these are all about. We forget about the significance of conjugation, right? Right? Conjugation's a big deal. Cosets, all of these things. And it's very difficult to make a lot of progress in the direction we want to go unless we sort of recover some of that. This happened in the general relativity lectures, right? There was a point where I said, you know, we've really got to dig into the idea of a manifold. And I think I paused, or this may have been in the middle of the What is a Tensor series. And I started a whole lecture series on just manifolds. I don't really want to start a separate lecture series, so I'm going to embed this in the Lie group lecture series. But we're going to spend however many lessons we need to really sort of review group theory in a way that it's intended to be a reminder, right? If this is the first place you've ever learned group theory, well, it's the wrong place, right? We're not going to teach it from scratch. We are going to kind of go back to the beginning, yes, but this isn't you've got to do the hard work, right? You've got to do homeworks and exercises, and you've got to get the definition in multiple ways, and you've got to learn all about subgroups and some specific groups, and you've got to get a lot of hands-on stuff. I'm going to sort of start with the hands-on stuff, and hopefully that it starts triggering reminders of memories about, in a good way, of course, about the past. The thing is, the cycle of all this stuff is, ready? It goes, you learn, right? Then you forget, and then you learn again, right? And then you forget again, and then you learn again, Learn, and then you either, by this time you die, or you know it, depending on how long this cycle takes, right? If this is every 10 years, you might end up in the die column. If you do it in a couple of years, you'll get to the know it column, right? If you're a teacher, right, you learn, forget, in 3 semesters of doing that, you know it, right? Regardless of what course you're teaching, 3 times and you're good. But, if you're talking about something that's a little bit afield from what you normally do, you may go through this cycle over a whole lifetime. And admittedly, each time you relearn it, it goes a little faster, so that's good. But this is the normal way the human mind works, right? Until if you're in a profession, you've learned, forget, and you know it, that happens, within a year if this is your profession to learn this material. So you know it pretty quickly. But if it's not, you still have to go through this, and it's just as difficult. Anyway, so we might be for some of you in the group theory thing, we might be in this second zone. For me, most of it I know, but some of it is actually hopefully in this last zone for me for group theory. It's a big subject, right? Group theory is a huge subject. You got to kind of decide what to focus on. For example, in this review, one thing I'm going to focus on is something called group presentations, right? It's not something I focused on or learned about much before, and I certainly know what a group presentation is, so I do have my first iteration, but this second iteration is going to be a little bit deeper even for me, so this is all good. The point is that if we don't go through this, the rest of the material on Lie groups is going to be a little weird. And also, one of the critical stories of Lie group theory actually has to do with dihedral groups, or they're called Cayley groups. And so I want to sort of focus on that. Okay, so that's our plan. And today we're just going to sort of start at the beginning and then just go as deep as we feel like we need to. And then when we're done, after who knows how many lectures, we'll get back on track with representation theory in its pure form. Okay, let's begin. I want to begin by showing you where I am going to get this latest sort of data on groups. And I say where I'm going to get my latest data, meaning I've studied group theory in the past. I've read a lot of books. I actually have an incredible number of books on group theory, which is really strange. I don't need the number that I have because they all say the same thing. But I've never really spent a lot of time with this Group Explorer, which is available on the web. Just Google Group Explorer 3.0, and you get this fantastic collection of all the smaller groups and different ways of looking at it. You get the library, these visualization options, and this section on homomorphisms. Actually, I really only can see these two. I'm not quite sure how to get at this yet. But the point is I'm using the resources from this to produce this lecture. In particular, for example, if you go to the Group Explorer and you activate it, one of the things you'll see, well, I guess what you actually see is you see this page. It's hard to see here because it's so small, but you have this definition section that looks like this. It's the definition, it's the order of the group, the definition of the group. And we're going to talk a lot about what this means. And then over here, for each group, they give you a link to the Cayley diagram, multiplication table, object of symmetry, and cycle graph. All these things are things we're going to talk about. But we're really going to focus on this definition of a group in today's lesson. And here I've just sort of blown up the definition of a group section. So what you see is you see the name of the group's order. In this case, it's a little bit not. Usually, I line these things up in order of groups of order 1, groups of order 2, groups of order 3. I have them all stacked up, and that's usually how they're thought of. The groups, all the groups of order 8, for example, are quite interesting, and we'll probably focus on all the groups of order 8 first, just because they're big enough to be really, really interesting, but they're small enough to be manageable. So we're going to talk about the group definition in today's lecture, but I just wanted to make sure you had a chance to see where these various charts come from. For example, if I go back into the material here, let me see if I can find it. For example, this is for the group, the dihedral group of order 4. You can see that you have the multiplication table, which came off of that website. You have the multiplication table that's kind of broken up by cosets, which is something you can do off that site. I don't think we'll talk about this today, but we will maybe in the next lecture. You have a list of all the subgroups, and we'll explain how they're depicted. You have this thing called the object of symmetry, which is fun. You have the cycle graph and the Cayley graph. All this came from that website. Okay, so with that in mind, I recommend you go to the site and have a look around. It's a lot of fun. And in the meantime, let's get started. All right, so here are those tables for one particular group, the group D4, right? And D4 is the dihedral group of 8 elements. So sometimes you'll see this written as D8, right? Because where the group order is down in the corner. D4 is, I think, reflective of the fact that the symmetry object of this group is a square, right? So their square has 4 sides, ergo they might call it D4. But regardless of its name, we're going to call it D4 because that is what the Group Explorer we're using called it. Now, there's 2 points I want to get across early. One is the idea of using group generators to create this multiplication table. And in this case, R and F are the generators, and every element of the group is expressed as a word, and that's the technical term, actually, a word written in those generators. And so that's an important point. And then the other thing is I want to make sure that we resolve sort of the confusion or the purpose of having an object of symmetry for D4. And I guess this is where I'll start. It is very common for people who've learned group theory one iteration through to think that, oh, we've got a square, and the square can be rotated and flipped and still be a square. Ergo, the square has this certain set of symmetries, and that set of symmetries is somehow reflected in a group we call D4. And the connection is usually in your brain, or in their brain, or in the straw man student brain that I'm creating, that the geometry of the square somehow is responsible for the group, right? And this, of course, is a prejudicial way of looking at it because we have geometric minds that see things in space very well. So we're very comfortable with the idea of a square and rotating it and flipping it. And so we think of this as the fundamental thing. The way we really need to think about it is that the square does indeed have symmetries, and those symmetries can be specified by something else in the world of mathematics called a group, and that group we've given the name the dihedral group in 4 elements. So the dihedral group in 4 elements captures exactly the symmetries of a square, but it's not that the square somehow produces this group necessarily, right? Now, obviously, they're so tied together that it's kind of absurd to worry about this little semantic point. But I want everybody to understand that the groups have to be thought of as existing in and of their own right. There's only a certain number of them, and we showed them, we showed all of them up through order 20 a moment ago. Those are the fundamental things. Finding objects of symmetry for those fundamental things is a bonus. And in some cases, it's actually pretty hard to find an object of symmetry for the group. And I'm sure that in many cases, well, probably in most cases, the object of symmetry is unknown. It's some unknown higher dimensional object. So in those cases where the object of symmetry is something low dimensional enough for our little brains to wrap around, we have this connection, but we can't allow that connection to make us think these groups are somehow bound to these objects. The groups are the groups, the objects are the objects, and the connection between the two is quite profound, but you can't favor one direction or another. All right, so the point of all that is to get you thinking of the groups as mathematical quantities in and of themselves, like each individual integer. All right, that being said, now let's go into the most abstract possible way of specifying this group D4. Now, you might think the most abstract possible way might start with this square, right? But it's not. We're going to use something called generators and relations to describe D4. And you can see the importance of this right away. Every element here is given in terms of R and F. So R and F have a special place in the way this table is written. R and F are not the only choices, right? You can do other choices, and in fact, we are going to, with D4, create another choice. But all of the subgroups here, too, are expressed in a very unique way. We have to understand what this means for these subgroups and this notation. So we'll get to that. But let's first figure out what is exactly R and F and how are R and F expressed in a mathematical way that captures this entire multiplication table without writing it out. So the multiplication table is pretty abstract, right? I mean, this is a very good and abstract way of writing down the group, but we're going to nail it down even more abstractly right now. Now, I think the first thing that's obvious that goes without saying is that the letter R and the letter F are arbitrarily chosen. The reason R and F are chosen for this example is because we're dealing with the symmetries of the square. And the symmetries of the square do, in fact, let's see if I have a square here, do, in fact, have rotations and flips. And so that's what we're dealing with, right? The rotation, the clockwise rotation, we're going to assign to the letter R. And I think the way we're going to do this is to flip about the vertical axis. Is going to be assigned to the letter F. Now, we'll talk about how to implement those later, but the choice of R and F here is already leaning into this intuition we have about that binds the dihedral group of order 4 to the symmetries of the square. So forgetting that for a second and just saying R and F are arbitrary symbols, right? We are going to write down this. We're going to say, we're going to put the two symbols that we're calling our generators. And we're saying that there's a group out there that has two generators. And every element of the group can be written as a word using those two generators. So if I write R and F together, what I really mean is R group operation, the binary group operation, whatever that is, on F, right? That's how we understand R and F being adjacent. That's no big deal. But RF as a product is a word with the letters R and F. So RFF is another word, and RFFR is another word, and RFFRRRFR is yet another word. And every one of these words is an element of our group, D4, right? Because we're defining the group D4. So, but not only is every element or every word that you could possibly write with the letters R and F an element of D4, every element of D4 is expressible in terms of these two generators. So already, whatever this group D4 is, it's got this one property that it can be, the entire group can be described with two generators, right? Now, there might be another group out there of order 8 that requires three generators, R, F, and say H, right? There might be a group out there of 8 elements that only requires one generator, R, right? We're going to pretend that we don't know whether or not that's the case right now, but after this is over, we'll look up all the groups of order 8 and see. But it's a property of this group that only two generators are required. Now, it so happens you could use 3 generators of 4. You can always use more than the minimum, but the minimum is an interesting question. So there's a minimum of 2 generators here. Now, if all it was this, the group with 2 generators, and there was no other information provided, right? Then this would be a group called the free group. The free group of 2 generators, right? Where any word arbitrary is part of the group. And it's obviously a group with an infinite number of elements, right? But we're not using the free group of 2 generators. Not every single one of these words is different, right? All of these words are definitely members of the group, but they're not all different. So we need to sort of capture the idea of the ones that are the same. So the way we do this is we specify the relations between the generators that are relevant. So the first thing we notice is that in this particular group, we know that R to the 4th power is equal to the identity. And we also know that F to the 2nd power is equal to the identity. So in terms of words, it means R equals E and F equals E. And the way we actually like to write this is a little bit tighter. R4 equals F squared equals E. Now, when you see an element whose square is the identity, that's called an involution, right? And I guess either F is an involution. I guess you could say F is an involute. I don't know. I've only heard involution, but that's just an interesting point. Oh, F is an involution. Another involution, by the way, is R squared, right? R squared is an involution because R squared times R squared is R, which is R to the 4th, which is E. So R squared is also an involution. Okay. I'm trying to get all these definitions and words out there to remind everybody of what those words were, because you probably heard most of these words before. So we have those two properties, and sure enough, if we look on our multiplication table, we see that R squared times R squared, which is R to the 4th, is E. And we also see that F times F is E. Now notice the way this table works is if you see R times F, you enter the table at R on the left, move over to F, and then you have the product. So the table reads row, column. Row, column is how you read these tables, the way they've set the tables up in the Group Explorer. So that's good. We know that so that accounts for some of these table entries, right? Some of the table entries right away we can account for. But what's important is that in the infinity of words out there, R, F, F, R, 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 F, 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 R, 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 F, right? There's an example of a word, a totally legal word. But we know everywhere we see four R's, we can just get rid of it. Let me do that in blue. We can get rid of the four R's. Everywhere we see two F's, we can get rid of it. If we see two F's, we can get rid of it. So now I have R, 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 F, R, F, and I see four R's, I get rid of it. So I have F, R, F. So I've gotten all the way down to F, R, F. So words can be collapsed pretty significantly just using these relationships, which take the generators and relate the generators to the identity. All right, so that's good. The problem, of course, is that if you look at the multiplication table, FRF does not appear in the multiplication table. We have the elements in the 8 elements of the group are R squared, R cubed, F, FR, and RF. And what this is telling us is that any product of these two elements can be expressed as it can be expressed as another element, right? That's how groups work. So if I'm going to name this group element R squared F, I better have an element on there that's R squared. Whoops. I better be able to square R squared F. So I better be able to do R squared F, and that's RRF, RRF. Now, none of this is going to help me shrink that word down, and that word doesn't appear in here. So there's another set of relationships I need to even get this to a point where every single time I construct a word, I end up in this table somewhere. So for the dihedral group, I need another relationship to define this group. And that other relationship is also presented it's part of the presentation. And the way the group explorer does is it writes it down as R, F, R equals, and then it says F inverse, which I find a little bit odd because if F squared equals E, that means F equals E, and that means F equals F inverse, right? Which is fine because it's an involution, right? But this is the way the group explorer likes to write it down, and it is the way I've seen it written down in others too. Not quite sure why they don't just call it F, but there's probably some reason out there. If you know, let me know. But anyway, you have RFR equals F. So now all of a sudden, with that and with these 1, 2, 3 relations, this is actually a different relation. There's a comma here. So that's a relation, and those are 2 relations. You can now take any word, R, R, F, 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 R, 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 F, R, R, F, F, and you can turn it into another group element that's one of these 8. And we can do this real fast. We know we cross out those 4, we cross out those 2, we cross out those last 2, and we end up with R, F, F, R, R, F, and then we cross out those 2, we end up with R, 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 F, right? And then we have now R, 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 F. And then what do I do? So now I know that, there's an inverse here, right? But I know that F equals F inverse, so this equals R, 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 F inverse, which equals R, 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 F, R, right? Because that's what F inverse is. And then I can now cross out these 4 R's again, and I get FR. And FR is, in fact, one of the elements of the dihedral group. So this statement here is, in effect, that's a weird turn of phrase that I don't actually like, but I do say anyway. This is the most abstract way of writing down the group. You list the generators, express how the generators are related to the identity, and then you express all the important relationships between the generators and each other. Now, there's a deep theory about this, right? Because the question now becomes, is I've kind of reduced this to mathematical symbolic statements. I mean, okay, well, what if I do f cubed and r squared and something like that? You know, what happens now? Is that a group? And have I found a way to create groups by just creating rules like this? And of course, the answer is no, you have not. You still have to hunt down and find the groups. You have to figure out what these relationships are. And so this is not some automatic machine to create groups using generators and relations. But every group must be expressible through generations and relations, and we are going to consider that to be the most abstract way of doing it. Now, how would you find such a group? Well, if you do have a symmetry object, right, you can now use the symmetry object to produce a group, right? You don't know if every group can be produced this way. It doesn't automatically tell you what the generators are necessarily. You have to think through all these things and then prove them for each and every group. And hunting down and doing this is called classification. You're classifying every possible group of, say, order 8. Maybe we'll do that. Maybe we'll go through all the groups of order 8 just to sort of demonstrate this process. But let's now go back to the connection between these generators and this object of symmetry. So the object of symmetry, we're looking for all of the motions associated with this square that preserve the shape, the geometry of the square. And we can tell right away, you know, through sort of an elementary intuitive examination of this thing, that if you take the square and you rotate it by 90 degrees, it's still a square. You rotate it by 180 degrees, it's still a square. All the rotations are not symmetries, because if you rotate it by, say, 45 degrees, you no longer have the same shape. You have sort of the same shape on its edge, like that. You have a diamond now. Now, you could say, well, that is the same shape. It's just the same, you know, modulo some arbitrary rotation. And there are ways of studying that, but we are not going to study that right now. We're looking for discrete groups where the shape, the orientation, it's all preserved. Now, that's a little bit weird, like I think I said in the introduction, because, you know, if you rotate this red square moves here, this blue square moves here, and therefore this object does in fact change because you've broken rotational symmetry by coloring the corners. But we do need a way to kind of keep track of how things move. Ultimately, because this is all going to be connected to permutation groups in the end, and that's an important thing to remember. And so permutation groups involve shuffling numbers around, and so you have to label the corners. And so we're not counting these colors as part of this symmetry process, just the shape. And so if we decide that we're going to call a rotation by 90 degrees R and a flip around the vertical axis F, then every symmetry of the square can be expressed as R and F. Obviously, rotation by 180 degrees is R squared, rotation by 270 is R cubed, which is also equal to R inverse, right? And R squared is an involution, so R squared equals R squared inverse, right? A flip by over this vertical axis equals its own inverse, right? So that covers quite a few of them, but then every word is just ultimately going to be one of the other symmetries that we haven't shown here. So for example, there's a symmetry across this diagonal, a flip across that diagonal, and there's a flip across this diagonal. If we call that D, and we call this D prime, we have those two axes, and then we have a flip about the horizontal, which we could call H. So there's these other axes of flip symmetry that are very similar to F, right? So we have to think about those too. So obviously, well, all these other things, R squared F and RF and FR represent D, H, and D prime. So let's just quickly make sure we get that straight. And then let's rewrite this multiplication table for D4 in terms of two different generators, right? two different generators. So let's do that. All right, so let's consider the flip. The flip asks f about this vertical axis. Now I'm going to take this group element, which we're calling f, and I'm going to say, okay, this is actually a thing that acts on the square. And here's my little square. So f is acting on the square. So I put f to the left of this little square symbol. So if I take the square and act on it with f, the result is a new square that has this green element moved to here, the blue element moved to there, purple element moved to there, and the red element is moved to there. And then if I want to take the next step and I want to rotate it by 90 degrees, I'm now rotating the new square that's been flipped by f. And now if I rotate it by 90 degrees, this red square, right, which originally moved to here, it's now rotated to there. Right? The green square, which was here, is now down here. So this is now green. And this is red. The red, remember the red was flipped and then rotated. So now it's back to where it was. Where this first thing is a reflection through f, and the second thing is a rotation back. And just so happens it lands back in the same spot. This purple ball was flipped and then rotated to here. Right? So this is now purple, right? And what happens to, then this blue guy was flipped and rotated back. So that stays blue, right? That stays blue. So this expression here, I now want to be able to write, well, that's RF acting on our square, right? So RF is now it's a group element, but we're treating it as some kind of operator on a square. This is an idea we're going to talk about later called a group action, right? This is a group action. The group element is now being interpreted as some kind of operator that does something to another set, or another, in this case, an object. And that group action is one of our first and important steps in understanding representation theory, to interpret group elements as though they are some sort of actions. Anyway, as you can see, in this particular picture, red and blue stayed the same, but purple and green switched. So this is a reflection about d prime. So I can now say that a reflection about d prime is equal to rf, right? Reflection about d prime is equal to rf. Now, likewise, the same analysis will show D is the opposite. You rotate first and you flip second. So I can now write D prime acting on the square, right, is really defined as RF acting on the square, which is R acting on F, which is acted on the square. Something like that. Likewise, H, right? We're calling that horizontal flip H. H is going to be R squared F, right? Which also, by the way, equals FR squared. It's kind of fun, but if you can work through this and you can see that we can rename RF, FR, and FR squared with D prime, H, and D. So let's go do that. Let's go back here and have a look at this. By the way, it's kind of fun to see here. We have H equals R squared F. But look, R squared F equals RRF, which equals RRF, and I throw in 4 R's over here, right? Because that's just the identity E, right? These 4 R's is just E, right? So I can do that. And then I take RFR, and I use the fact that RFR equals F inverse, which in this case equals F. And so I collapse RFR just to F, so I have RFRR like that. And then I do it again, RFR equals F, and I get FR squared. So R squared F equals FR squared. So it kind of it commutes. And that's why when you look at the table, if I enter the table at R squared and go to F, I get R squared F. But if I do the opposite, if I enter the table at F and go to R squared, I still get R squared F, because R squared F and FR squared actually commute, which is kind of cool. Okay, so that's another example of how we use the generators and relations just to show a few different things about the group itself. All right, but now what was our plan? Our plan was to just replace all of these things with these statements here, right? So let me just take the time to do it. All right, I think I've done it there. And so now we've given every group element its own name. Well, almost. I mean, we gave most of the group elements their own name, but I guess we're still playing with r squared and r cubed, right? So if r is 90 degrees to the right, r cubed is actually 90 degrees to the left. So we could then go in here, we could call this r prime because it's actually 90 degrees to the left. And then r squared is a 180 degree flip. So we could call that r bar, right? R bar. And I'd have to do it everywhere over here too. R bar, R bar, R prime, R prime, R prime, R prime, R bar, R bar. Now, everything is in terms of its own name, although I'm still using, I guess I kind of screwed that up in the sense that, well, D and D prime, they're related. All these are rotations. I've literally just changed cubes to different things. I mean, this is a very non-substantive change, which is kind of the point, right? It's all about naming things. But you can see why the generators are actually pretty good. It explains everything in terms of just two group elements in this case. It's because it's capable of using two group elements because this group is unique, is just by the laws of, I want to say by the laws of mathematics, but that's kind of like saying the integers by the laws of mathematics. I mean, the integers are what mathematics is. And the same with these groups. These groups exist because they do. And we've now figured one of them out, the D4 group. But I want to emphasize that the group generators there are really the most abstract way. And every group element is its own group element. Even if it's written in terms of generators, that doesn't make it any less important. And in fact, to really emphasize this point, we can choose two different group generators. Let's choose, for example, a diagonal flip, D, and the regular flip. So we're now going to use the flip about the vertical axis and the flip about, I guess I've chosen D, right? So the flip about that. Let's use those two to generate the whole group, right? Let's see how does that sort of change our group presentation if we choose two different generators. All right, so I've kind of written it all out here, so let's see if we can make some sense of it. First of all, D equals FR. We've kind of established that. FD then is FFR, but F by this rule here is 1, so that equals R. So FD is R. DF is now FRF because we substitute D for FR, right? So we get FRF. We add 4 R's on the front end and then we pull out the known generator for RFR, which is F, right? Because we know that RFR is F inverse, but F inverse is F itself because F is an involution. So we end up with, we get rid of that, we end up with that, but then F's an involution, so that goes away, so you end up with R cubed. So DF equals R cubed. And then you kind of keep going this way, right? So we have DF, so now we can create FDF, all right? We've created D, we've created FD, we've created DF. Now we've got FDF. Now we can't create FFD because F's an involution, it would just be D. So we can only put F on the other side. We're only allowed to use the two generators, right? But DF, or FD is R, so this is RF, but we know RF is D prime. So that's an easy one. And then we take FD and we put D on the front of it, but FD is equal to R, so this ends up being DR. And I think I kind of went forward and backwards a few times. So D is FR, so you end up with FRR, which is FR squared, which is H. So it's the H flip there. And then you kind of keep going until you see if there's a pattern, right? FD ends up being R squared. FD with an F at the end is f r inverse. So I guess df is r inverse. df is r inverse. Did I say that? Yeah, df is r inverse. So you end up with r inverse, but r inverse is equal to r to the third, right? So r inverse is the same as r to the third. So you end up with fr to the sixth, and then you know r to the fourth equals I. So you end up with fr squared, which is another expression for h, right? And so now you've built up the h that way. What do you got next? Well, then next you have, ultimately you have fd, which is r cubed, because fd is r from up here, right? And then, well, now we would just add another f. You can't add the f on the front, so you got to add it on the back. You get three r inverses, df, df, and df, but each of those is an r cubed, so you got r to the ninth. That breaks down modulo r4, so you get fr, so that's d. Well, you're kind of getting redundant now, but if you add another d on this, you end up with r to the fourth, and you get e, which is actually sort of another important relation. So we've now broken down everything in terms of the generators d and f. So I could, in principle, rewrite this table, right? And instead of using the generator r and f, I could use the generator f and d. Now, how would I do that? Well, I leave f alone. Which one of these guys here represents d? Well, d is fr. So everywhere you see an fr, I would write a d. So, for example, here I would write, I'll just go a capital D, right? D, D, fr. Everywhere there's an fr is just d. Fr, d, d. Anywhere else? Yeah, all those are d's. And now I have to look at everything else in terms of those guys. So I know that r, right? I know r is equal to fd, right? So r is now fd. So everywhere you see an r, you write fd, fd, fd. Okay, I think I got all those. Everywhere you see an r squared, what do? You write fd, fd, right? fd, fd. So all the r squares are fd, fd. So I think I got that down. And then you just proceed this way for everything else until everything on this chart is in terms of f, d, and the identity e. So this is obviously not as clean as r and f, right? R and f is, you can kind of use these powers, but every time you have a power of f or d, it immediately goes away, right, to I. So using all involutions is a bit of a mess. However, the big takeaway here is that we can write this as fd such that, this is really important now, f squared equals d squared equals I. And then the relationship should be fd to the fourth power equals I, right? And this is another presentation of the dihedral group, the D4 dihedral group. And the reason this is important is that this can actually be generalized. This can be generalized. And the generalization for this, that takes this expression that we've done for D4 or for D4 and boosts it up for other groups. Remember I said a moment ago, I think I said earlier, this, you can't just create random statements in here and then hope a group pops out. But we can take this and generalize this and produce a whole class of groups, an infinite class of groups. And that should make sense, right? We know that the dihedral groups, right, they're based on these symmetries of these polygons, right? Triangles, squares, right? And then let's see if I can do a pentagon, right? Like that. And there's an infinite number of those, so there should be an infinite number of dihedral groups, right? So what is this generalization? And let's have a look at that. And then we'll call it quits for today. Well, not too much to say about it, except that if I erase this 4 and replace it with an n, then I have now created the presentation of the flip and rotation symmetries of an n-gon. Now you got to be a little careful because, as I said, we're doing D4. This would often be called D2n, where n is the number of sides on the n-gon. So this, our group, the one that we're working with, would normally be called D8. And so you got to be a little bit careful about the convention that's going on. In fact, I'm pretty sure if you look this up on Wikipedia, you're going to see the D2n convention, right? I like Wikipedia a lot. I probably should have stuck with their convention, but I like the Group Explorer even more. So this is the generalization that I was so dramatic about. I changed that one little number. But notice there's still 2 generators that are involutions. Also, notice that this second one is also an equivalence to I, right? So, heck, obviously, I could have just written that as, let's see, I just erase the I here, right? And then I just go FDM equals I, right? Like that. So in this case, there's only relationships with I. It's all presented with relationships to I. Now, I could have taken the other presentation. Where'd I have that other presentation? So here is the other presentation. Notice I put an M up here to be consistent with the M here. So this is this is the dihedral group for some n-gon, right? Or an M-gon. M as in M as in meteor, gon, right? But this, look, if I just multiply on the right by F, I could have written RF equals I. And that makes perfect sense because this is really D prime equals I. But of course, D prime is a flip, so it's an involution. So of course it equals I. So the point I'm trying to make with all this is that we can write, we could have from the beginning put everything in terms of the identity without a relation between the generators. I stressed it was a relation between the generators, right? RF, well, I guess I should undo RF squared equals I. So everything could have been put in terms of I. And presumably that's, as far as I know, that's always possible. But there may be multiple relations. So it could be totally inefficient to do it or too tricky or whatever. But there's multiple presentations for these things. So we kind of saw that this was sort of the most efficient presentation. And it's actually pretty easy to generalize too, right? All you do is really that M up there is the only thing you need to really worry about. It turns out this generalization, however, gets a lot of traction because it is related to something called the coexter groups. And that is something we will need to talk about to understand the representation group theory of Lie groups. And that's really important. This goes into coexter and Deichen diagrams and things like that. So we're going to spend a lot of time on this later on. So we might spend some time talking about the coexter groups and groups generated by reflections. But anyway, the purpose of this lecture was to get your head back in the game regarding these objects, right? So in the next lecture, we'll talk a little bit about cycle graphs and Cayley diagrams and some of the critical subgroups of all this. All right, see you next time.